Okay, so now that we've talked about power series in section 11.9, what we want to look at next is how certain familiar functions can be represented as a power series. Now, the idea of representing a function in multiple different ways is not a new concept. So we deal with this a lot in trigonometry, actually, when we talk about trig identities. Just as an example, if you consider the function f of x equals cosine squared of x, we have a power reduction formula that you learn about in trigonometry. Cosine squared is equal to 1/2 times 1 plus cosine of 2x for all values of x. These are equal to each other. So what this means is that these are two different ways of representing the exact same function. And in some cases, one representation may be more useful than another. It just sort of depends on what you're using it for. Power series, it's kind of the same idea. So remember, a power series is a function of x. You can think of a power series as kind of like an infinite degree polynomial. That's the way that we talked about it in 11.8. However, it turns out that these power series can be equal to familiar functions like trigonometric functions or logarithms or things like that, if you choose them correctly. So right now what we're going to do is talk about some of those familiar functions and how they can be represented as power series. And then starting in 11.10, we'll come up with a more wide-reaching method for coming up with power series representations of certain functions. So to start with, here's one we've already covered. The function 1 over 1 minus x is equal to this power series, 1 plus x squared plus x cubed, and here it is in summation notation. It's only equal to this power series, though, if the absolute value of x is less than 1. We derived this because we saw that this is actually a geometric series for any value of x that you plug in. X is filling the role of the common ratio for that geometric series, so it has to have an absolute value less than 1 if it's going to converge. But as long as the absolute value of x is less than 1, these two things are equal to each other. Now, oftentimes, when you have a function like this that's equal to a power series, we refer to this side, this 1 over 1 minus x in this case, as the closed form for that function. And basically what that means is it's a way of representing that function with a finite number of terms. Whereas here we have the same function but with an infinite number of terms. Sorry, my dog is in here. He's making a bunch of noise. So I want to examine this a little bit more closely. So, sorry, my dog is being so loud right now. So as long as the absolute value of x is less than 1, these two things are equal to each other. And this series, if you think of the absolute value of x as being some number less than 1, as you raise that number to larger and larger powers, the value that you get is significantly smaller. It's much closer to 0. So for example, if x is equal to 1/2, 1/2 to the second power compared to 1/2 to the 20th power. 1/2 to the 20th power is an extremely small number. It's very close to 0. So what we are gathering from that is that most of this sum comes from the first few terms. And then after a while, each term becomes very, very small in how much it contributes to the sum. So if we were to cut this series off at any particular point and take the nth partial sum, for example, then we can see that 1 over 1 minus x is approximately equal to a polynomial of this form. So it's kind of worth looking at the graph of 1 over 1 minus x and the graph of this polynomial for various different values of n to see how they compare to each other. And that's what we have right here. So my function f, which is 1 over 1 minus x, is this red curve right here. This, I know, is the graph. The graph of this looks like a hyperbola. So we're really only getting one branch of that hyperbola right there. And then all of these polynomials here, I can see kind of hug that function really, really closely as we are near 0. And then they kind of spread out as you get away from 0. But the higher degree partial sums of this thing look like they remain closer to f for more of this graph. So here's S11, for example. It's this green graph, this green curve. It hugs that red curve really closely, whereas S5, the 5th degree polynomial that I could put into this form, Still does closely approximate the red function, but it spreads out a little bit faster than that higher degree term. So this is also kind of just showing that the more terms that we include here, the better of an approximation to this function that we get. Okay? All right, so we single out this power series representation for this function because we can use this exact power series representation to get power series for several other similar looking functions. So we're going to remember this. 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus so on and so forth until to infinity, basically. All right, let me show you some examples where we use that representation. So I want to come up with other power series for other functions. This is 1 over 1 plus x squared. It's a different function than what I had on the previous page, but notice that if I were to rewrite that as 1 over 1 minus negative x squared, this is the same thing as 1 plus x squared because those negatives would cancel out. But now I have 1 over 1 minus something. And over here, I have 1 over 1 minus something. If I take the negative x squared here and I substitute it in for the x here, I can do the same on the right-hand side and substitute a negative x squared in for all of the x's here. The result will be a power series for this function. So remember, 1 over 1 minus x looked like 1 plus x, except now I'm going to write negative x squared, plus x squared, except now it's going to be negative x all squared, plus negative x squared cubed, and this continues on and on. This is the same thing as 1 minus x squared plus x to the fourth minus x to the sixth, and then so on and so forth. So clearly you can see that there is a pattern here. It's an alternating series, and all of my powers are even numbers because of how these simplified. But this is a power series for that function right there. I can put that in summation notation as well. This is the sum as I goes from 0 to infinity. It's an alternating series, so I'm going to have a negative 1 to either an n or an n plus 1 here. It looks like n is going to be the right choice because when I plug a 0 in, I get a positive first term, which I should be getting. And then my x's are raised not to the power of n, but to the power of 2n, because they're all even numbers. So you can see if I plug a 0 in, x to the 0 is 1 times negative 1 to the 0 is 1, so I get 1. If I plug in a 1, I get negative 1 times x to the second power, which gives me my next term, and so on and so forth. So this is a power series representation for this. Now we're not done, because with a power series, you need to come up with an interval of convergence. And remember, going back to here again, going back to here, this power series only converges when the absolute value of x is less than 1. We came up with the power series on the following page by substituting negative x squared in for that x right there. So I would do the same. I would substitute it in for that x in the inequality, and let's see what that gets me. So this is true as long as negative x squared has an absolute value less than 1. Okay? But the negative here goes away with that absolute value, and when I square something, it comes out positive anyway. So another way of writing this is just x squared is less than 1. And then this is the same thing as the inequality x is between negative 1 and positive 1. So this is my power series representation. This is my interval of convergence. I could go through and check the endpoints for this. However, well, yeah, let's check my endpoints actually. So if I were to plug a negative 1 in, x equals negative 1, what are we going to get here? Well, I'm going to get negative 1 to the n times negative 1 to the 2n. And notice the fact that there's a 2 here means I'm always going to have an even power. So that thing right there is going to just be a 1, and then this is going to alternate between positive 1 and negative 1. I get 1 minus 1 plus 1 minus 1, and so on and so forth. So we have seen that series before, that series that alternates between positive and negative 1s. This diverges. And it's easy enough to see that when x is equal to 1, I get the exact same series. this also diverges. Now that I checked that because we've been in the practice of checking those endpoints for our intervals of convergence starting the previous section. However, we don't actually need to go through all of that work because over here, this power series, we already show converges when this is a strict inequality, but not when it's equal to 1. And so by simply substituting negative x squared in for that x and then solving and getting this inequality, I don't need to do any additional work. I don't need to actually check these endpoints. I did this one just because it's good practice, but for the rest of the examples, we're not going to bother checking those endpoints. Let's try another one. We want to find a power series representation for 1 over 4 plus x, and then also find its interval of convergence. So this is not quite in this form. It is going to help me to change that plus into a minus and make it minus the negative of something. But there's another issue. The fact that there's a 4 here is a problem because this power series representation assumes that we have a 1 here, not a 4. So what I'm going to do is factor a 4 out of my denominator and pull it completely out of the rational expression. That would be like a 1/4 times 1 over. That 4 now looks like a 1. I want to subtract something that's negative to account for the fact that I have a plus where I really want a minus. And then if I factor a 4 out of that x, what's left here is x over 4. Okay? So this thing is of the form of this expression here. And where I have an x, I'm going to be substituting a negative x to the 4th. So this is the same thing as 1/4 times, I'm keeping that 1/4 out there, 1 plus negative x over 4 plus negative x over 4 squared plus negative x over 4 cubed. Goes on forever. Okay. This is the same thing as 1/4 times 1 minus x over 4 plus x squared over 4 squared minus x cubed over 4 cubed, and so on and so forth. I'm not going to make that a 16 or make that a 64 because it's more helpful to see a pattern here since I want to write this in summation notation. This is 1/4 times the sum from I equals 0 to infinity of, we have an alternating series, which means we are going to start at -1 to the n here, just like the previous example. And then if you notice, I have an x and a 4, x in my numerator, a 4 in my denominator, and they keep being raised to the same power. We're going to have x to the n over 4 to the n. Now I'm going to do one additional step here. This 1/4 on the outside, there's nothing wrong with leaving it out, but I notice if I were to bring it back in and multiply it to this expression, my 4 to the n is going to become a 4 to the n plus 1, which you might look at that as slightly simpler than what we have up above. So I'm going to do that. -1 to the n, x to the n, 4 to the n plus 1. I could write this series in that way. Okay, how do we deal with the interval of convergence? Well, the interval of convergence is going to take, normally it would take x in absolute value, make it less than 1, but instead of x, I'm using a negative x to the 4th now. Okay, that's got to be less than 1. The negative is going to go away because I have an absolute value there. 4 is already positive, so it doesn't need to be in that absolute value. This is the same thing as saying that the absolute value of x over 4 is less than 1, which is like saying the absolute value of x is less than 4 when I multiply both sides by 4. So my interval of convergence is this. X is between -4 and 4. Interval of convergence, power series. All right. So far, so good. Now take a look at this next one. We want to find a power series representation for x to the 5th over 4 plus x. So this guy, at first glance, it's the least like the function that we started with over here. It's the first time I have something other than a 1 in my numerator. But it turns out dealing with this is not hard at all, because I can write that as x to the 5th times 1 over 4 plus x. So basically just pulling the x to the fifth out front. And then I can use the fact that I just found a power series for this exact function right here. So this is equal to x to the fifth times the sum from 1 to infinity of -1 to the n, x to the n, 4 to the n plus 1. And I can take that x to the fifth and treat it like it's a constant basically, and bring it in, multiply it to this, which will give me the sum from 0 to infinity of -1 to the n. This x to the n, I'm multiplying it by an x to the fifth, which turns into x to the n plus 5 over 4 to the n plus 1. That's my new sum. By multiplying the previous power series by x to the fifth, we're not changing its interval of convergence at all. So I also get to use the interval of convergence that I already found previously. There's my power series, there's my interval of convergence. All right, looking pretty good. All right, so the next thing I want to do is talk through this theorem, and then I think starting in the next video, we'll look at some examples that use this. But this is an extremely useful and powerful theorem, and it actually kind of explains one of the major reasons why we want to represent functions by power series. It'll become a little bit more prevalent in the next section, but we're going to show some of the usefulness of this here as well. So basically what this theorem says is if you have a power series, and here's one of those very general power series. This one is centered at A. And if we have a radius of convergence that is greater than 0, which means it converges for more than just one value, then the function f of x, defined as the function equal to that power series, so in other words, this would be a power series representation for that function, is differentiable, which implies that it's continuous, on the interval negative or a minus r to a plus r. This is part of the interval of convergence for that power series. Notice that this does not include the endpoints, even though this power series might include the endpoints in its interval of convergence. So we're not assuming the endpoints belong here. But this power series is differentiable, and we differentiate it using what we call term-by-term differentiation. So if you recall, we've been saying that you can think of power series basically as an infinite degree polynomial. As long as we're operating on the interval of convergence for that power series, you can differentiate a power series as if it were a polynomial. So in other words, this constant term goes away. This C1, when I differentiate, is all that's left here. When I differentiate this term, the 2 comes down. 2 times C2 times x minus a, using the power rule. And then 3 times C3 times x minus a squared. You notice I'm applying the power rule to all of these terms here. Now, that's probably what you would have guessed would happen, but we don't actually have any differentiation rules that say that we can do this. If you go back to Calculus 1, where you learn about your differentiation rules and properties and things like that, you're taught that the power rule works. So if you want to differentiate a monomial, something like x to the power of n, you can apply the power rule to that. You're also taught that the derivative of a sum of functions is equal to the sum of the derivatives of those functions. Which would seem to justify what we're doing here, except for one important caveat to that. What you cover in Calculus 1 never says that those can be infinite sums. When you go through those properties and you prove those properties, it's always assumed that you're talking about a sum of a finite number of terms. So we don't get to automatically assume that things that happen for a finite number of terms will always happen for an infinite number of terms. We've already seen that with our convergence tests and things like that. But this theorem says that power series, fortunately, do have this property on their interval of convergence. You can differentiate them the way you expect that you would be able to using the power rule. Not only that, integration works that way as well. If you want to find the antiderivative of f of x dx, this function here, you do it by integrating term by term. So if you notice that c there is the constant of integration that we always get from this, plus c naught times x minus a, plus c1 times x minus a squared over 2. That's like what we would get by integrating just this term by itself. So we call that term by term integration, and we call this term by term differentiation. Now, in addition to that, not only can we differentiate and integrate these power series, but we automatically get the exact same radius of convergence when we do that. So notice that if I take this series and I differentiate it, or if I integrate it, I'm getting a new power series by doing that. But the radius of convergence automatically travels with that. So if the radius of convergence of this guy is r, then both of these will also have a radius of convergence that's equal to r. That's really nice because that means you don't have to go through the work of finding a new radius of convergence when you get these new series. You can just carry over the old one. So in the next video, we'll do a couple of examples where we use this idea to come up with new power series representations for different functions.